From the UK, and good morning and good evening to our worldwide group of delegates. I'm Andrew Dunsmore. I'm the Industry Engagement Manager at Leicester University, and I'll be your chair for today. Welcome to the fourth webinar in this series on the second International Symposium on Application of AI in Metallurgy and Materials. In the previous three webinars, the main focus has been on the excellent research being developed around the world in this important subject area. This webinar is titled The Application of AI for Industry 4, and it will focus on how industry is responding to this challenge and the opportunities it will present. Just as a matter of course for the procedure, we will hold the Q&A session at the end of the discussion. But if you want to ask a question, if you just post it in the chat box in the Zoom, and then we'll pick that up at the end during the Q&A. So now I'd like to formally open the proceedings, and it's my pleasure to introduce Professor Ivan Chukin of the University of Leicester. He's the Professor of Applied Mathematics. He's head of the Visual Intelligence Lab, the School's Director of Research, Next Generation Digital Intelligence, Deputy Director of Artificial Intelligence, and Associate Editor of the Communications in Nonlinear Science. So he's ably qualified to give the opening remarks. So over to you, Professor Chukin.
Oh, thank you very much, Chairman. First of all, I would like to say that it's a great pleasure and privilege for me to open this part of the forum in Leicester. Artificial intelligence in Leicester is one of our strategic research teams, and it cross-cuts through all the colleges. So this is evidenced by the university's investment in our new Data Analytics AI and Modeling Center, AI's significant role in Leicester's Space Park, and Research England funded a Meteor project with more than 30 industrial partners participating in this initiative, and in many excellent initiatives in life sciences as well. So Leicester puts a great value in these technologies, and today we will be focused on metallurgy and materials and applications of AI in these areas. Recent years have seen tremendous explosive progress in AI systems and their applications. We all witnessed this progress, from autonomous cars and superhuman performance in Go and chess, to translation of text and medical imaging, and importantly also manufacturing. Most of this progress was possible due to continuous accumulation of vast volumes of data and empirical knowledge in our more and more digitalized society. These vast volumes of data accumulated wealth of knowledge in statistical learning theory and growth in computational capabilities created extraordinary opportunities for data-driven AI. All of a sudden, problems which were hard to even think of solving within traditional frameworks due to their complexity or lack of first principle knowledge became approachable. Extraordinary volumes of data, a previous obstacle, turned now into a gold mine, and statistical learning theory from the past century became a mining pick, enabling to circumvent and replace the lack of first principle knowledge with learning from data. And we are at the center of this revolution. Now, let me please briefly introduce this current forum here. So following the success of the first part, and in particular the first international forum on the application of AI in metallurgical and materials engineering at the University of Science and Technology of Beijing in August 2019, the second aim was originally planned for the summer 2020, but due to COVID, it was the decision from the organizing committee to make this meeting online. So, this forum now presents a series of weekly webinars for 4 consecutive weeks, and this is the 4th. The aim of the conference is to disseminate the latest research activities in the application of AI and data-driven approach to material design and processes optimization. Ultimately, the goal is to accelerate the development of intelligent manufacturing technology and in material and metallurgical industry, and to provide international platform for discussion by scientists, engineers, technologists, and industry leaders. There are many ways in which AI can offer benefits to scientists and end users, and application of AI in metallurgy and materials can enhance materials quality, improve process efficiency, reliability, and safety. And importantly, these methods may include the latest manufacturing systems, intelligent devices, inter-machine communications, and data analysis. We have a great list of talks and presenters today on the application of AI for predictive processes optimization, scalable predictive maintenance, and also for the applications at NISCO. I am giving now the floor back to the chair now. Thank you very much.
Thank you very much. Thank you very much, Professor Chukin, for those remarks. I think that sets the scene well for this webinar. I'd like to move on quickly to the first talk, and I'm delighted to welcome Fucheng Li. So Fucheng Li, he graduated from the University of Wollongong in Australia with a master's degree in advanced information technology research. He now works in the IT department of NISCO, and he served as system administrator and database administrator and participated in the development of NISCO's information systems. He's the principal researcher for the research and development of artificial intelligence in NISCO, and we're looking forward to his talk, which is titled The Application of Artificial Intelligence in NISCO. Over to you. Thank you.
Thank you. Hello, everyone. I'm Fucheng. I come from Nanjing Aero and Steel Company. My topic is the application of AI in NISCO. Nanjing Aero and Steel Company, NISCO, is a giant venture of Hong Kong-listed company, Fucheng International and Nanjing Aero and Steel Group. NISCO involves the manufacturing of ferrous metals and the sales of the steel materials. NISCO has a total asset of 50 billion RMB, and in 2019, NISCO achieved an operating income of 130 billion. The total profit in 2019 reached 4.5 billion RMB. And the application of AI in the steel industry, there are 4 layers. The first one is the digital production. The second one is virtual reality factories, and the intelligent management. On the top one is the intelligent decision system. Today I will share the 2 cases in NISCO. The first one is the performance prediction of X70. The second one is the intelligent inspections of scrap steel. This is the first one, physical performance prediction of X70. Steel production process is complicated, time-consuming, expensive. Each of the links needs to enforce strict quality control. Statistical process control system has been widely used in aero and steel industry. However, the SPC system can only give the warnings of parameter in production process, and it cannot predict the actual values relevant to the product quality, such as product physical performance. And the main goal of this section is to explore the prediction of physical performance in steel production process by using continuous variables such as temperature, pressure. These variables are regularly recorded in the system. prediction system is achieved by defining the task as a traditional regression problem, which involves applying one or more continuous input to forecast a desired output. And the challenge of performance prediction, the quality control of steel production is very complicated during each stage of the process. Um, uh, the prediction is very challenging. The reason is that each process is very complicated and a change in values of a process parameter may have a great impact on performance. At present, the performance of value is obtained through physical and chemical tests on sample of a steel product. However, the development of IoT, big data, AI has brought a new possibility for performance testing of steel production. Machine learning methods have a great potential to discover the knowledge out of a vast amount of data with a sustainable increase in manufacturing data response stories. Uh, okay, system framework for NISCO. There are 4 layers for the system framework. The first one is the raw data set, contains historical observations, manufacturing execution system, and the labs execution system. The data from these 2 information system and some data from the sensor. The second layer is data extraction and pre-processing. In this layer include analysis of processing the abnormal data, filling of missing values, and remove duplicate data. Data normalization method also include to transform these variables between 0 and 1. Data modeling and analysis platform. In this layer, we use the ETL tools and the real-time acquisition function to extract the information from historical data sets and input this data into our data warehouse. Here we use the SAP HANA database as our data warehouse. It built in the analysis tools such as R language, Python, and finally, based on the data modeling and analysis platform, production process analysis, quality tracking, data mining, and machine learning algorithm is a main part of this layer. And we developed the steel control layer on the top. And data availability. Most companies have established the information system at the early stage, such as MES, SES, LES, ERP, EMS. In this study, the data sources are primarily collected from the existing information system of Nanjing Aero and Steel Company, which are MES and LES systems. We choose the 11 basic machine learning models as our baseline to build the ensemble machine learning methods. They are learner models, SVM, KR, KN, RF, and so on. Ensemble machine learning models combine multiple different machine learning models to improve the prediction performance. Bagging, boosting, stacking are the most common approach used to generate an ensemble system for solving the different problems. They set 55 parameters such as continuous casting, rolling, cooling, chemical elements, of each product was obtained from the MES system, and the performance labels, yield strings, tensor strings, allegations for each product was obtained from LES systems. And this is our experiment result of execution 11 baselines. From here, we can see the XGBoost is the best for the single machine learning method. And combine the models with averaging method and the stacking method. From here, we can see the ensemble machine learning method is better than the single machine learning method. This is our main findings in this work. The combination strategy is as follows. For the result, two ensemble models outperform the single ones from all metrics, all evaluation metrics. The averaging combination of SVM, KR, LGBM, XGBoost is better than other ensemble method under the single models. And our work that had been applied in the product lines, besides the physical performance prediction of X70, the hardness prediction of 45 magnets still has been run stably in the product line, and the accuracy of the model is 89%. Okay. And the performance prediction of Q195 series has also been run steadily on the product line. The accuracy of the model is 19%. The second part is intelligent inspections of scrap steel. Current status of the scrap steel inspections. First one, the working conditions for inspectors is not very good. There is an enormous amount of dust on working field, and the quality inspectors need to get off the truck frequently during the quality inspection process, which is a high risk, and each inspectors has a different understanding of the scrap degrees based on its own knowledge. The last one is it's hard to recruit the inspectors. A computer vision system, according to the current status, using computer vision system to inspect the scrap steel, which can standardize the evaluation rules, and it also can save the cost, improve the working conditions. Here is a challenge of the script steel grading. The first one is the clarity of the picture. The weather has a high impact on the outdoor image collection. The images have a great difference under the different weather. And the night images are blurred, which is a challenge in the recognition task. The second is the composition of the scrap steel. The composition include industry scrap, the abandon of shipboard, and a scrap steel from the normal life. This results in the diverse scrap steel from both the thickness and the quality. The last one is the difficult of grid regulations. Differences in the implementation of scrap steel standards by each product department lead to the difference in the labeling of the scrap pictures. Scrap steel intelligent grading process. This The first one, when the truck driver swap their card on this machine, imagine collection trigger device, and then the camera start taking pictures every 30 seconds. Then we got the picture, and we will see if there is a crown magnet in the picture. If there is a crown magnet in the picture will be removed. If there is only the carriages in this picture, and the picture will take in the carriage area. And then we use our algorithm to recognition of the scrap steel and the impurities of the carriages. And then we combine the impaired mode of deduction of impurities. Finally we got the grid of the scrap steel and the proportion of the impurities. As I mentioned before, this is the equipment and the process, which equipment we use and which algorithm we used it. We have collected more than 10,000 images of the scraps steels. This includes different scenarios of the interface of the crown magnet, different carriages, different weather, different time in a day, and so on. This is a picture was taken during the day, and this is the picture taken late afternoon, and the picture taken in the rainy days. And we use the Euro wizard network as our basic algorithm. The structure of Euro wizard algorithm is as the following: darknet 53 neural network is used for the backbone, and the blue component represent the basic components in Euro 3. Here is the main outcome of our system. The model has tested the scrap steel over 300 carriages, and the test result compared with the non-grading result. The comparisons result are as the following. The accuracy of material type recognition could be 83%. The error of deducting impurities shows below here. And the future work. Object detection algorithm applied in this research experiment shows that this type of algorithm cannot accurately grade scrap steel. Therefore, we will use the image segmentation algorithm to grade the scrap in future work. And the current picture focus on the scrap steel in entire the carriages, which make it difficult to distinguish the grade scrap steel. In future, we consider use the zoomed scrap steel images. This is because such picture can more clearly distinguish the scrap steel grade and the type of impurities from the picture. Thank you for your listening.
Thank you very much, Fucheng Li. Very interesting talk. Having spent over 30 years in the steel industry, it's great to see that we're moving from sort of passive analysis to more dynamic prediction. And also the things like the scrap area, and that is a really key area in that to reduce that variability. So thanks for that interesting talk. Can I just remind everyone that if you want to ask a question, if you can post it in the chat box, and we'll pick it up at the end. Okay, I'd like to move on to the second talk today by Dr. Tom Kirk, of Foresight data machines. So Tom is a physics undergraduate at University College London, and then did a PhD in condensed matter physics at the London Centre for Nanotechnology. He started the business Foresight data machine 2 years ago, and it's focused on applying modern AI research in combination with traditional engineering in order to optimize industrial processes. So I'm looking forward to your talk, Tom. So over to you.
Yeah, thanks a lot. Okay, so hi everybody. As Andy says, I'm Tom from Foresight Data Machines. In a nutshell then, what my company tries to do is this statement here: optimize efficiency, quality, and productivity using AI-powered predictive control. So we kind of have this vision to control steel-making processes in like a perfectly optimized way using online automatic predictive planning. So of course, in order to do this, we have to take the cutting edge AI techniques from academia and try to apply them in the industrial environment. And this obviously raises some serious technical challenges. So that's what I'll talk about today: what challenges must be overcome to achieve this vision. And I'll do kind of two main sections. First, I'll do a case study with an electric arc furnace, and then I'll just talk more generally about some of the obstacles and the solutions. Okay. So first then, the case study is going to look at optimizing the efficiency and productivity of the electric arc furnace using predictive control. That statement in itself, it might be quite self-explanatory to a lot of people, but just to cater to like a varied audience, I'll break it down a little bit before I show the results. So if you imagine right now that we're sat at the side of an electric arc furnace and we're melting some material. And what I've got here is a plot of temperature on the y-axis and time on the x-axis. So this is the temperature of the scrap and whatever is in the furnace. So imagine we're sat at this start time here, and we've just taken a temperature measurement with a probe. Okay. Now our objective is to get from this temperature to the target tapping temperature at around the tapping time. And of course, we want to use as little energy and as little time as possible. We want to achieve that as efficiently as possible. So we apply some power and we wait a while till we get to the tapping time. Then we check the temperature again. Maybe we find the temperature is good now, and we've probably taken a path like this, although we can't monitor the temperature perfectly. Now, this would be a good case. Here we would tap the melt and it would be fine. Of course, in practice, it doesn't always happen perfectly like this. What might have happened is when we checked the temperature at the tapping time, the temperature was actually up here a little bit, maybe just a few degrees, nothing you really think about in real life. But of course, what's happened is you've wasted a little bit of energy there because you've heated the steel more than you actually needed to. Or in an even worse case, you might check the temperature at the tapping time and find that it's cooler than it needed to be, in which case you now need to apply some more power and take a little bit longer than you expected. So you didn't quite guess the power profile correctly. And of course, even in the case where you got the temperature just right, you could have taken different paths to get there over the course of time, right? You could have used different power profiles or put in different amounts of oxygen and There's so many controls. And so it's very difficult to figure out how to take this optimum path every time, right? In an ideal world then, what you would have, of course, is when you're back here and you take your first temperature measurement, you would be able to like almost instantly run a load of simulations that consider all the different control options and run, online virtual trials, basically online virtual trials, and then look at each of those and then choose the one that led to the most efficient and productive outcome. And then say, cool, this is the control program we're going to use right now. And you'll be doing this constantly in response to all the different data coming from the furnace and everything. Okay, so this is the kind of thing that we want to get to is basically model predictive control. Of course, the reason this isn't done at the moment is because it's extremely difficult to create a perfect predictive model that can be really, really fast and allow for all the different variables and be really accurate. Is not been solved before. So I'll show you the results we got. So if you are seeing this plot now, Andy. Yeah. Okay. So if you look at this top figure here, just bear with me a second. So if you look at this top figure here, this is the same as this is the same kind of plot as the one that I was just showing a minute ago. So it's got temperature on the y-axis and time on the x-axis. And so imagine again, we're sat next to the furnace. And this line here, where we go from black to purple, this is the current time. So I've kind of paused time for a second and I'm sat just here, okay? Now, the line, the black line and the purple line is the prediction of the temperature of the melt according to our algorithm, okay? So it's kind of predicting what it thinks the temperature was in the past and what it thinks the temperature will be in the future. The red dots here, they are temperature measurements that were taken in real life. So this is real process data. At the moment, those measurements, they are in the future. So they haven't been taken, the algorithm has not seen those yet, but I'm just leaving them on there for reference so that you can see that the predicted temperature trajectory is accurate, right? So it hasn't seen them yet. Now, one really important feature of this temperature prediction already is this shaded area, the thick shaded area. This is such a key theme. It's something that I want to kind of labor a lot, is including some confidence in the prediction, because if you're going to use this thing to make decisions, you really need to have a good idea of how confident you are. At this point, no temperature measurement has been taken. We're before the first temperature measurement in this batch, so the confidence is very low. The uncertainty is very thick. It's very high. Okay, so the AI algorithm is saying, I don't really know what's going on, but this is my best guess. Now, if we go forwards a few minutes, okay, so this next plot is going forwards a few minutes. Now we have received the first measurement, right? We've passed the first measurement of the temperature. So now every couple of seconds, the predictions are updating. It's taking the new data on and it's going, okay, this is what I think this is my updated belief. So the predicted temperature line is quite similar, but the thickness of the uncertainty has decreased a lot. Look. So that the AI algorithm is much more confident now because it's seen one temperature measurement. It says, yeah, okay, I know what's going on. So that's the prediction there. And of course, seeing things like this in practice increases your confidence in the system. Now, if you imagine you're the operator then and you're sat at the side of the furnace, what you really want to see is not quite this plot. You want to see something a bit more like this, okay? So this is taken at the same time, but now in the future, I've got 3 paths instead of 1. Each of the 3 paths then is a different possible outcome that could occur each one corresponds to different control settings. So it's saying you could apply a lot of power or not much power or very low power. And of course, there's a lot more going on behind the scenes. I'm just showing a very reduced view because of confidentiality, of course. So what's happening is it's going to predict for each of these 3 suggestions it's making, it's predicting the tap time and the total amount of the total energy efficiency that would result. So the operator can look at their options that the AI is suggesting and say, okay, we need to tap in this much time and we want to maximize efficiency and and they can make this decision kind of in cooperation with the AI, depending on what the current demands are operationally. So this is the kind of system we propose. Of course, eventually you could have fully automated control where we're able to run thousands of different possibilities and choose the perfect one every time. That's totally possible. So the key information about this then, these plots I'm showing you now, I can tell you these are from a case study we did at ArcelorMittal, and we had a lot of the accuracy was very successful in that case study. When we're predicting the current temperature, the temperature right now, our model is about 5 times better than the previous state-of-the-art model, so quite accurate. And we're getting close to being as accurate as a sensor. So as the actual temperature probe, we're almost as accurate as the probe now. So it's getting pretty good. And as I say, crucially, the simulations are fast enough that you can run many of them every second and quickly consider different options and plan the most efficient route. The thing we're most proud of, though, in the system is this dealing with the confidence issue. So it's not necessarily how good is your average accuracy, it's how bad is your worst prediction, right? That's like actually one of the most important things when you apply things in industry is if you have quite good average accuracy, but very occasionally you have absolutely terrible predictions that make like no sense at all. This is a disaster in industry. It's not a problem in academia, but it's a disaster in industry because you can't trust the thing, right, to make decisions if this is the time that it's giving something totally crazy. So we managed to eliminate these pathological predictions. Like our worst prediction ever is still acceptable. Let's put it like that. Yeah. So I'll jump back on the slides. So that's the case study. And what I want to do now then is, by the way, I should say, we estimate that using a system like that with the electric arc furnace can lead to energy savings of a few percent is the current estimate. Of course, it depends very much on the case at hand. So now what I'll do is I'll just make some general comments about the obstacles that you face when you're applying the cutting edge academic tools in the industrial environment. So a lot of this will tie back into what I just said in the case study. So I've got like this illustration here of the academic environment with the Go board because, famously the game of Go was used for a lot of these cutting edge machine learning algorithms. That was mentioned in the introduction, actually. And I've got a picture here of a electric arc furnace operator representing the industrial environment. Of course, the two environments have got different characteristics and they present certain technical challenges. So let's have a look at what they are. We think, we kind of talk about 3 key obstacles that I think occur in most cases when you're lifting a tool from the academic environment to the industrial one. Okay, so they're in this order. This is the order they actually occur in practice, is the data challenges, modeling challenges, and integration challenges. So I'll just go through them one at a time briefly. data challenges is easy. Everybody, well, it's difficult to solve, but everybody knows this one. It's very important. In academia, you often have perfect data. You can often even just generate data at will. And in industry, often there's no data at all in the beginning. Like, you know, people just haven't been saving it or storing it correctly or whatever. So this is obviously a fundamental problem. The good news is it's quite an easy problem to solve, because typically in the steel industry, the capital equipment is already capable of collecting the data. So this is only a case of some software, some data infrastructure, and like actual operating practices. So like just take the data from the PLCs and store it somewhere. Like, so this is, it's a bit silly, but solution here is just collect the data. Okay, we have to see that as part of the process of applying AI, and not just look for cases where we already have the data, because that's just how it is. Second challenge, this is a bit more technical now, are the modeling challenges. One of the biggest modeling challenges that's different from the academic environment typically to the industrial environment is what I've just called here, the academic problems are typically static, but in industry, the data is dynamic. And what I mean by that is, I've got here the case, it's a very famous case in machine learning, is you train an AI algorithm to try and recognize handwritten digits. And you can train these to be really, really good. In fact, you can train them to be better than a human. You can train them to be amazingly good at recognizing handwritten digits. When it's an awkward one that might be a 5, it might be a 6, etc. They're very good at it. Now, so on the face of it, if you just looked at the average accuracy, you would go, wow, this thing's better than a human. Now, of course, the funny thing is that I've got a picture here of what would happen in industry in the equivalent thing. Is one of the pictures is a chicken. This is a bit of a joke, but it's totally serious. An academic pointed this out last year. If you pass a chicken picture to one of these digit recognition algorithms, it says this chicken is the number 5. And it says it with 99% confidence. Okay, you can show it a picture of the number 5 and it says, okay, it's the number 5. I'm like 75% confident. But you show it a chicken, it says that's a number 5, I'm sure. Now, it's kind of funny, but this is a huge problem in industry, because in industry, there's a lot of chickens. You never have, it's not, okay, this is the data we trained on, and this is the kind of data we're always going to get. What happens in industry is sensors break, or we get new equipment, or new materials, or new operators. There's lots of things, and your solution has to be reliably and robustly analyzing this new data all the time, dynamically, without a human checking if there's any chickens in there. So this is actually a huge problem, and a really serious technical problem. For me, this is like the hardest thing. On the same vein, in academia, you'll report the average prediction often, like, we get 99.999% of the numbers correct. Whereas in industry, I already said this in the case study, the worst prediction that you ever make is like the most important thing. So, of course, these two things combine to give a really difficult problem. How do you deal with these chickens and not have terrible predictions? The solution that we pose to this is that you have to use different tools with the AI. So we use, first of all, we use tools from Bayes theory, which might be familiar to some of you. That's a set of tools that can be used for estimating confidence. So what that means is that maybe if we create an algorithm and we get given a chicken, we can't say, oh yeah, that's a chicken, because we're not used to seeing that. But at least we can say, hang on, I definitely don't know what's going on here. Like, you know, don't trust anything I say right now, you know. So, and that's the kind of confidence that we were showing in the case study with the different regions, with the shaded region of our prediction. So tools from Bayes theory, very important for confidence, for dealing with broken sensors, new materials, all of that kind of stuff. On the same vein, we use theoretical physics as well. What that means is that by using basic physics equations, we make sure that whatever answers we give are always respecting the basic physics of the problem. And that further reinforces against having crazy AI answers that just don't make any sense and that damage confidence in the product or whatever, or in the solution. And then lastly, we use the AI, and we use that for what it's good for, which is giving this really high average accuracy, like superhuman average accuracy. So it's the combination of all three of these that we think that's not focused on much in the academic problems because it's not relevant, but I think it's the key in the industry applications, is bringing all the tools to the job. Third type of challenge then is the integration challenge. By this, I just mean, you know, you've made an AI solution and now you actually need to use it in the industrial environment. And it's only going to be as good as how well it is used. If you make a perfect solution and it never gets, or if you can get perfect prediction accuracy and nobody ever uses the prediction to make decisions, then it's totally useless, right? So integration and adoption is another big, it's actually like a technical challenge. And for us, we think the solution to this is continuous improvement software updates. So instead of having a static solution that you deliver where you say, okay, this is the specification of the furnace control algorithm, let's say, and like aim for this and let's make it, and then it's finished. What we propose is it's more like the process of getting, you know, continuous updates on your phone or on your laptop every couple of weeks. You know, you just do a first iteration of the furnace control algorithm, and then you talk a lot to the key stakeholders, to the operators and to the engineers, and you keep iterating on the software and delivering improvements very quickly. So, you know, in a short space of time, it might be unrecognizable from the first version of the software, but there's a really strong feedback loop there, because it's impossible to just guess how it should be in advance. That's all I have to say really. Is the case study, the key technical challenges. It's all about confidence for us, dealing with broken sensors, noisy data, buy-in of the users, and the key there, we think, to most of the technical challenges is the combination of tools. Don't just rely on AI as a magic bullet. It's AI, physics, and the Bayes theory all together. So as a final note, if you want to collaborate with us in any way, shape or form, we're very open to industrial partners for pilot projects. And we're also really interested in academics. We've even got job opportunities. If anybody's interested, please don't hesitate to get in touch. Thank you.
Thank you very much, Tom. Interesting, thought-provoking topic. It's particularly interesting in that I've been able to translate from academia into businesses and exploring some of the challenges in doing that. So that's excellent. Can I just remind everybody again, if you want to raise any questions, and that, just put them in the chat box and we'll pick them up at the end. Okay, so we're moving on to the final talk in today's webinar. And I'd like to introduce Johnathan Bonner is the pre-sale engineer for Sensai. So Johnathan, he was, over the last 10 years, he's held multiple positions in the industrial condition monitoring field, working for a number of blue chip manufacturing companies around the world. In his current role, he's the lead pre-sales engineer for the UK and the US. And just to mention about Sensai itself, it's headquartered in the UK, with regional offices in Germany, France, and America, and Japan. It's a leading global industrial software company for asset performance management, and it helps global industrial organizations to save millions of dollars in unplanned downtime and maintenance. So a very good topic for today's talk. So over to you, Johnathan.
All right, thank you. Let me just get this up. Lovely. So today we're pretty much going to be talking about how artificial intelligence has made scalable predictive maintenance a reality. We've already had a bit of an introduction to myself, but my role as pre-sales engineer effectively means that I try and describe the complexity surrounding the buzzwords of artificial intelligence and machine learning in as simple form as possible. Most of my experience in this field has been gained within Sensai, and that is because Sensai delivers scalable predictive maintenance. So if that's the one thing that you take from my entire talk, is that we deliver scalable predictive maintenance. Now, any predictive maintenance solution needs to have some core values. First of all, it needs to be easy to use. It needs to be a solution that is used by maintenance professionals, not data scientists. It also needs to be easily deployed from 1 factory to 10 factories to 100 factories. That needs to happen quite rapidly. As with anything in life, it needs to be financially beneficial. And in Sensai's case, we have a guaranteed return on investment, which makes it an even better deal. But the vision of predictive maintenance is effectively trying to detect the early signs of degradation, as you can see on the left, long before it turns into a catastrophic failure of an asset. But not to do this just with one asset or one type of asset or a set of critical equipment within a plant, but to do it for the balance of the factory. That means your heating and cooling systems, your motors, gearboxes, conveyors, overhead cranes, your extraction systems, all of it. But to be truly scalable, you need to be able to do it across every single factory. So from factory 1 to factory 19. If you take Alcoa or Tata Steel as an example, these factories are in charge of the full life cycle of their product, from mining to smelting to sheet metals to finished products such as cans. And in Tata's case, they have automotive division. So their steel sheets then go to the automotive plant. So this means that any company or most companies would have a wide range of different asset types that they need, and they need a predictive maintenance solution that can cover all of their environments. And when we start to engage with clients, what we find is that 80 to 90% of their maintenance team time is spent on reactive maintenance. Now, this gives a lot of cost associated with downtime. And there will, of course, be a certain level of planned maintenance, but that also comes with costs such as a high inventory and stock requirements. And then obviously there will be proactive. So this is more lending itself to the route-based condition monitoring. However, this does take highly skilled professionals and lots of man hours. So we want to move our clients on a journey through these spaces to get to the predictive and prognostics. So how do we do this? Well, Sensai, first of all, treats every asset as unique, whether it's a primary crusher, a motor, HVAC, a wind turbine, whatever it is, we treat every asset as unique. We do not build models per asset type. The reason being, if you spend 2 to 6 months building machine learning models for an asset type, and you need to restart the process again when you move to the next asset type. And this doesn't lend itself to be scalable. So Sensei actually has an automated way of creating a unique model per asset as an individual. Why do we do this? Well, let's imagine 3 robots, just as an example. They were bought at the same time from the same manufacturer and implemented on the same line. These robots may have been attached to the floor in a different way, or the floor structure may be different. They definitely would have had different maintenance activities and maintenance staff working on them. They may be exposed to different temperatures or particulates within the air, and their production life cycle would definitely have been different. All of this together may seem like an insignificant difference between these assets, but we know that this makes a significant change in the failures or potential failures of these assets. So what Sensei does is we take condition monitoring data from all machine types. We build a baseline or a unique digital fingerprint of what we believe normal behavior is for this asset. And compare this normal fingerprint with live data 24/7. And when you do this, what you end up with is detection, effectively condition monitoring, being able to spot the smallest signs of change. Yes, trying to spot the smallest amount of change when comparing normal to live data. If we were to add in failure modes and failure data, we then are able to give you diagnostics, which is your predictive maintenance piece. Further to that, we add in ongoing maintenance data, and we have the availability of prognostics. Now, prognostics is the science of understanding the remaining useful life of an asset, but effectively, it's moving away from predicting bad health and moving to giving you a window of confidence of good health. Are you going to be able to run an asset for the next production cycle? And this is all done through the transfer of data. So if you imagine a factory floor or industrial environment, you'll have a range of different assets that will have data coming from them. Whether this data is being stored within the PLC or coming from external sensors. And then this data goes somewhere to data storage, potentially a factory historian. It's important to note that there's a body of work at this point, at least for Sensei. And this is turning condition monitoring data into condition indicators. And this is a form of aggregated condition monitoring data, which directly indicates the condition and signs of degradation within an asset, and is minimally influenced by operational change. These condition indicators then get sent to Sensei, and we sit completely within the cloud. However, we also form a closed feedback loop into the CMS system, because getting that maintenance data and the work orders back into that information back into Sensei enables your predictive and prognostics. And this is Sensei at a glance. I understand that there's quite a bit on the page, but I will take this complexity and explain it in a simple way. So we take the condition monitoring data along with operational data, such as different processes or control information, and the maintenance data. And that then goes to our core platform, where we do a bit of data pre-processing and feature extraction. We also want to add in a bit of context. So what is the machine types? What is your asset mechanically doing? What is the work event history of this asset? We want to assign the asset a criticality and know what the production schedules have been for it. We then apply our artificial intelligent machine learning algorithms, and I apologize for all of those buzzwords. But effectively, we have a set of algorithms that deal with anomaly, trend, and step change detection. This is your basic form of condition monitoring. So those algorithms deal with that. We can also input expert knowledge in the form of thresholds and rules, maybe even ISO standards. A basic example would be if you didn't want a component to go above 60 degrees, we could set in a threshold at 50, and as soon as it was violated, we could notify you of that. Then we also have prognostics, and for Sensei, prognostics comes in 3 parts. First of all, we can we can forecast when we believe you're going to violate your threshold and where it would get to. Second, we can give you a window of 28 days of when we believe you're likely to need to intervene with an asset. So on which day in a 28-day window you'll need to perform work. And then we also match that to previous known failure and give you recommendations of what work you should do based on previous rectifications. We take all this, we run it through an attention engine, which then gives you an attention index score. Now, attention index is a level of concern. How much attention do I need to give an asset at any given time? And we present you these assets in order of severity from their attention index calculations. And a case is open, so that's how we notify you of this. We also then give you evidence directly underneath this case of which component or which measure has been alerted to, has affected your attention index score. Again, we're trying to focus your attention to the component that needs your attention on this asset. And that's why we are scalable. All of it sounds very complex, but most of it's automated. And that's where artificial intelligence comes in, to make it scalable. So these are some of the big success stories we have within CSI. The first being Nissan. In 2016, we engaged with them on a project in the UK with 30 assets. They had a remit to reduce downtime by 50%, which we did. We also achieved the return on investment in less than 3 months. Today, we are monitoring over 10,000 assets in 8 parts globally, and we've saved multiple millions in unplanned downtime in every site. Schneider Electric is also quite interesting because we integrated to the Wonderware and Aviva historians. Sensor has been brought into Schneider Electric's ecosystem, and within the Schneider Electric plant, we've reduced the direct maintainer involvement by 20%. And I think for a talk today, Alcoa is probably the most relevant. So Alcoa had a challenge. And the challenge was throughout their plants, they had a wide range of asset types of different ages and different supporting systems, whether that's the historians or the CMMS systems surrounding each factory and each asset. And Sensei was brought in as a chosen predictive maintenance provider because we have an ease of integrating and working with a range of different systems. And because of the factors that I've spoken about already, we can work quite efficiently and effectively with assets of any age. So if we look at it, in 2018, we had a competitive tender and we won against 12 different competitors. In 2019, the project started in Fjorddal, Iceland, with 50 assets. On the project of those 50 assets, Alcoa achieved a return on investment in 3 months. And this year, we are monitoring over 1,000 assets with a global expansion in progress. Now, Alcoa have had to hire no new people to first implement or scale our solution. They've also installed no new sensors. So we've used the data that is currently available within their plant. And in 2019, they achieved the return on investment 10 times over. So I believe there are questions coming up a little bit later, but thank you very much.
Thanks very much, Jonathan. Another interesting talk in a key area of maintenance with the length of time these assets are in place, maybe 20, 30 years. It's important that maintenance is maintained throughout that life cycle. So just many thanks to the speakers. We're going to come on to the question and answer session now. Yeah, if you just give me time to look up these questions. So first question is for Fucheng Li from Ravi S. What data was collected for the hardness of steel? Fucheng, are you there?
Okay. The data should be the chemical element for the hardness prediction.
Yeah, it says what data was collected. So is the data purely chemical analysis for the hardness?
Chemical elements. Chemical elements for the for the steel grid.
Mm. Okay, thank you for that. And then a question for Tom. Oh, sorry, I just moved to the answer box. So may I ask what features were included in your temperature modelling? Is the first question. It's a two-part question. And for control options 1, 2, and 3, what process variables were included in these control options? So the first one is, what features are included in your temperature modelling?
Yeah, so in the temperature model, we've tried different numbers of features. Basically, we can get decent results with very few features, or we can use like a very large amount of features and get better results. The most important features are just the typical ones you would use in a traditional model, like the energy balance and the mass balance, like what masses are you putting in and what energies are you putting in, and can you measure any of the mass coming out and any of the energy coming out. For the control options, so we can evaluate different control options for like any variation of any of the things you have control over. So like whatever you can control as an operator or an engineer, we can like imagine those different options and like whatever complicated path you want to use. So it's not just one fixed point for each one. You can put like any trajectory. Like the time scale of the model is like 1 second. So you can do any complicated path you want. So the way you choose those different options is based on your particular operational constraints. So yeah, so that's how we do it.
Yeah. So I mean, I know, Tom, just following on for that, the process, one of the process variables you were looking at was temperature in the electric arc furnace. That, does your model predict anything in terms of the variability of the temperature or the temperature at the slag metal interface or anything like that? Is that
yeah, we are working on that. So you know how the temperature has some, I kept going on about this like confidence thickness. It's like we've got this area of temperatures that we predict. So part of that range of temperatures is the spatial variation of the temperature in the furnace. So if it's predicting a range of temperatures, that means it's saying in the furnace that there could be this whole range.
What is the main error?
The main reason is that it's inspectors grading the scrap based on their own experiments. So when we labeling the picture, sometimes we cannot get the actual grade of the scrap. So the accuracy is not very high.
Okay. And then currently you collect 10,000 images of scrap steel at different situations. If you further increase the number of images, will that improve the accuracy?
Yes, I think if we got more pictures, the accuracy will be improved. And at present, we try to collect more pictures, especially during the night.
Okay, thank you for that. So here's another question for Tom. You identified integration and adoption is the key to transfer the academic research to industrial work. Do you have recommendations to enable a smoother transformation?
Yeah, I have two. One that I did not mention is to try and get all of the different stakeholders engaged. So like in the kind of project we talked about, the operator themselves should be engaged, and the technical engineer, and then even like the manager of the melt shop, because all of those people will interact with the project. And if any one of them doesn't care or like, you know, isn't engaged, then it can be a critical problem. So I think all of them. And then the only other point is the one I mentioned, which is making, don't try and get it right first time. Don't try and specify it without trying it. Just try and get something as quickly as possible, and then just keep iterating it based on the feedback of all of those stakeholders.
Okay, thank you. And another one for you, Tom. Is your temperature model purely based on production data, or is it still combining with the conventional model?
No, yeah, it's not just learning production data. It has real, has a little bit of conventional modeling in it. Plus, we use neural networks as well. So it's neural networks and some conventional modeling together.
Okay, thank you for that. That concludes, I think, the questions that we have in the chat boxes and the Q&A boxes. Can I pass it over to the panelists and to the presenters? Do you have questions to ask the other presenters? So
I think, Andrew, we have one more question.
All right, can you just read out?
Yeah, I mean, to Johnathan, you gave an example of aluminium company, and I wonder whether you could tell a little bit more of the work. I mean, give us a bit more detail of this aluminium work.
Sure. So when we started, what we would measure, the assets, the 50 assets that we were monitoring at Fuadong were all related to the wastewater treatment side of things. That was because they had high sludging problems, lots of wear out on their gearboxes, motors that were doing massive changes on their motors and their irrigation systems quite a bit. So we were able to extract data, I believe it was current and temperature information from these, from the extraction system, or the majority of it anyway. And we then, so we would take that data, we asked them to aggregate it, so to come up with their condition indicators. The process of that is to take your raw high frequency data, interrogate it, and then you can come up with your condition indicators. So we asked for a maximum and average every minute, and along with running states and loaded states. And with that, we were able to predict a full range of different failures on the different sets of equipment for their wastewater. And then the rest of the project moved through into the plant, so into the actual processing, the heating and smelting. But unfortunately, I don't have that much information on those.
Thanks for that, Johnathan. Just one question from my point of view, and that I was quite surprised to find that you found with Alcoa that you didn't need any more sensors. Is Sensei able to go into a plant and actually sort of back engineer and actually say what sensors and data would be needed?
Yeah, so it's if you imagine it's like a three-step approach, or at least that it is for me. We want to first of all understand the assets that we're going to monitor. So if we get like a basic schematic or a description from the engineers who work with these assets, then we want to know the failure modes. So let's go back into your historic CMMS system. Let's find out what work has been, what work you've been doing on these assets over the last 3 years. Right, it's a good time. And from there, we can look at what data is available. So if, let's say, 30 measures are available, we may only need 5. And that's the approach that we take with all of our clients. If we can see that it's quite clear that we don't have sufficient measures or sufficient data for these assets, we will then recommend that you install further sensing solutions. However, we always say, let's work with what you have. even if you are happy with 75% coverage, get your return on investment first, and then focus on getting a higher fidelity sensing. So that is our approach with all of it. And with Alcoa, it just hasn't been necessary.
Right.
Not to say that it won't. With the global expansion, you never know.
Okay, thank you for that. Are there any other questions then? There's none on the system. Anybody get any other questions? No? Okay, so I'll start to bring this to a close. Professor Dong, who's championed this, do you have any closing remarks?
Probably not. Just thank you all, and then for attending this meeting, and also for the speakers who gave these excellent lectures. And also, I also thank organizing committee and then for your hard work in organizing this in a very smooth way. Right. Thank you all. Right.
Okay, thank you very much. I'll bring that to a close. Thank you for a successful and interesting and thought-provoking session. Thank you.
Thank you.
Thank you.
Thank you very much. Thank you.